just be there, provide advice or whatever. But without further ado, we welcome Chris.
Thank you very much. It's great to see all of you here. Thanks for coming today. Very briefly, this is an experiment in professional learning that the TDSB is actually trying out. And so I teach in the mornings, and I have the rest of the time of my day to help out teachers in whatever way they find helpful. So we're trying it out, and we're seeing how it goes. Sandy's been one of my customers. So today, I want to share with you what I've learned about teaching the topic of motion and forces, putting it into a new framework, mental framework. And I want to begin by introducing this young woman here. Some of you may be familiar with her exploits. She was certainly in the news a lot about 2 years ago. Penny Alexiak, gold medalist from the Rio Summer Olympics. And she's the star of our grade 11 motion unit. So she's the first thing that our students see when we start the study of motion. And because her performance was so awesome, and because of the connections we could make to our physics class, I contacted the sports scientists who work with her at the Canadian Sports Science Institute, and they very kindly gave me some of their data from her gold medal winning race, including the video footage that they put together. So, this is the footage of her swim. Now, this is not the color commentary from the CBC. This is just their camera from the viewing gallery. So it's a very different perspective on things, but let's watch it carefully from the point of view of a scientist. Here we go. So she's in the white cap in the middle there. And there you have it, her gold medal winning race. Now, from our point of view as sports scientists, let's ask ourselves this question. We're going to have a 1-minute discussion. What could we measure about Penny in this race to give her feedback on her performance? She's young, they're expecting her to improve even more, and so what could we measure? So turn to the neighbors at your table and let's have a quick discussion. 1 minute, go. My school has a very thriving swim team, so this discussion gets very animated. So just a quick check from you folks. What are some of your ideas? Let's give it the 5-second summary. Anybody like to share? What could you measure? Rebecca?
I said starts and turns and her stroke rate.
Stroke rate, yeah. Ashley?
Your split times or how, like, your speeds during, not just like the whole race, but like for like at 10 meters, or you could do a 25, like whatever distance you wanted to cover in the first 20 or the last 20 or the third.
Great, great. Split times, Gary?
You have a red mark, or you could, there's a red dash.
There's red beads on the boys, yeah.
Take the time from the distance and then measure how the changes in distance are.
Great, great. Anything else? The time off the block? Yep, yep. Fantastic. Now, there's lots of possible things that we could measure about her. Let's think about this statement here. She swims the race with a constant velocity. How reliable is this statement? Turn your neighbors, 1 minute, go. Okay, thank you folks. So I can hear some of you saying, you're kind of looking at me suspiciously. What? Why is he saying something wrong here? What's the trick? trying to fool us somehow. What are your thoughts? How reliable is this statement? I mean this in all seriousness.
For parts of the race, yes. Not for the whole race.
Oh, okay. Are there any parts that are particularly poorly described by this statement?
Obviously the turn.
The turn?
The beginning and the end.
Maybe the beginning and the end? Are there any parts that are perhaps well described by the statement?
I would imagine it seemed like most of the strokes when she was stroking. There's the first part she pushed off and just like fluttered for a while, and then.
Thanks. So, a statement like this could be wrong, but it could also be right, depending on how we focus our attention on the phenomenon that we are trying to study. And just in case you're curious, here's the data that the Sports Institute sent me. And you can see it's it's pretty freaking straight. Mine would go like this. Except, did you see that? So when it comes time to study some phenomenon, we have to decide our mental approach that we're going to take to do that. And this is our idea behind scientific models. Did you know Einstein was ripped like that? little known but true. Now, when scientists routinely deploy models in order to help them understand the world, and think of a model as a set of ideas, a mental framework, the purpose of which is either to explain a set of phenomenon or to help us make predictions about it. And that statement that I gave you should come from a clearly defined scientific model. This idea crosses so many domains of science. We can construct models to help us visualize and understand what is happening inside a cell at a molecular level. We can construct models to help us visualize what happens to a building in the New Zealand earthquake. And we can construct models that help us to track, this video didn't work, can track dust particles from the Sahara going across the Atlantic and creating the hurricanes that have wreaked havoc in the United States this past year. Models are very powerful tools, and they are the primary tool for doing science. But how often do we talk about it in our classes? So this is an important new element in my approach for teaching the topics of forces and motion. Okay, here we go. Let's engage. All right, so what defines a model? What ideas do we need to have in there? And we've had some of them raised as part of our discussion here. In the previous workshop, if you were here for Nathan's workshop, we talked a lot about the idea of a system. We need to be clear, what are the objects that we are keeping track of, whose properties we want to measure? All models have a critical set of assumptions that help us decide when those ideas are valid or useful. That initial statement that I gave you is useful, but not all the time. And here's the final piece. They are valid for certain intervals of time. So that statement is a very, very good description of her motion if we focus on certain intervals of time. So the assumption that she moves with a constant velocity can be a good one. But we need a clear reasoning process and set of language that we can use with our students in order to talk about this and help them refine their thinking about the physical phenomenon we are asking them to study. So, one of the core ideas here, the interval of time, is based on the idea of events. This was a term that I never used in my physics class until about 10 years ago. But I've realized that it's one of the most crucial but missing pieces of the way that I formerly taught physics. An event, it's one of the simplest ideas in all of physics. We often forget to talk about it and help our students think about it. Something that happens at a certain position, at a certain moment in time. Hardly gets simpler than that. And then you're ready to define an interval as that interval between two events. This is one of the most important ideas that has helped to clarify my understanding that I share with my students and to help them think more precisely about their work. And I'll be giving you a number of examples of this in action today as part of our discussion. So, we have to train our students in choosing events. How do you describe an event? What is an event? So, possible events are, we very commonly choose them when the acceleration of an object or a system changes. Perhaps when its direction changes, or something significant happens, right? The runner passes the finish line. And it's usually the problem, or whatever the scenario is, that helps us decide which are the relevant events, because there could be many, many of them. So, let's practice this. I have a few situations here, or descriptions, and I'd like you and your neighbors to decide which of these is an event and which is an interval. My students constantly struggle with these. I'm sure you'll do better. Go. 1 minute, go.
The extent of the finish line. I mean, there's a point when the runner starts passing and a point where he finishes passing. and the finish line has perhaps a small but definitely a discrete distance.
Great. That is fantastic physical thinking. And in our model of this situation, we would have to make appropriate assumptions in order to then decide, are we going to treat this as an interval or an event? Great. So, let's take a look at a common one that my students trip up on. They all say this is an event. Like the ball hits the bat, bang! It happens. And this is what I show them.
That's way too fast to see. At 10,000 frames per second, you'll see the regulation hardballs.
So there you have a slow motion version, and I asked the students. So if we think of this as a pair of events, when does the collision begin? And we go through frame by frame, and I see, okay, it's when the ball makes contact with the bat. Event number 1. And then you see it squishing, it unsquishes, and then it leaves contact with the bat. Event number 2. This is an interval. A collision is a process. This is an idea that my students have a lot of difficulty with. Whenever an object's velocity changes, that takes time. It's a process. So we do a lot of practice of describing these ideas. Now these are examples of what I call the hidden curriculum, what physics education researchers often call the hidden curriculum. They are pieces of our understanding as experts, pieces of our expert understanding that we very seldom teach. Why does that happen? Sometimes it's because we don't even realize that those pieces of our understanding are there. If you take a look at an expert, and if you take a look at their skill sets and their mental processes, by and large, the skills of experts operate very fluently, almost instantly. And we can very easily forget the ideas, the skills that we use when we try to make sense of our world. And because of that, we fail to break apart those ideas, understandings, and skills, and provide opportunities for our students to recognize that they exist, and then to practice them in meaningful ways. So this is an example of hidden curriculum. Another reason why we sometimes don't teach this is because we say, well, we just expect the students to pick up on this as they go along. Right? They just need enough practice. And then they'll start to figure this stuff out. Well, we can't approach education in such a haphazard way, hoping that students more or less randomly stumble upon the key ideas and pieces of understanding that we want them to develop. We have a responsibility as teachers to break this apart and create a learning environment where they have a very high probability of developing these skills, rather than just hoping they arise by happenstance. This is really important, a really important part of our personal philosophies of education, because as teachers we need to have a genuine mindset that we are expecting success in all our students, vast majority of our students. And while we often say things like this to ourselves, we often say, on the other hand, that, well, this is physics. Right? And not everybody's going to get it. So it's kind of normal that half the class doesn't understand. That's not a proper excuse for not doing our job as carefully as we can. Because what we're learning now as a community of physicists and educators is what it really means to teach something very, very well. So it's like you're playing a video game and you unlock this whole other level. And that's what we're doing in teaching. We've unlocked this level where we realize, oh, there's all this other stuff that we can do, which will really help out our students. So our failure to do this has the strongest effect on the students who enter our classroom and ask themselves questions like this. Do I belong here? Can I be successful in this class? There's many reasons why students might ask themselves these questions. They might not see themselves as somebody who will grow up to be a highly educated person. They might not see themselves as a possible future member of this community of scientists, engineers, mathematicians. So students who are from traditionally disadvantaged backgrounds are extremely susceptible to leaving our courses because these questions are very quickly answered when we teach them in a traditional way that leaves out so much of the important practice and instruction that they need. In particular in physics, if we survey our female students and we ask them to measure their self-efficacy, this is a term that psychologists use to describe your personal sense of, if you're given a physics task to perform, that, yeah, I can do this. I have confidence in my ability to figure this out, to get the job done. And if you ask male and female students to rate their self-efficacy, we see a huge discrepancy. Male students have, by and large, a very high self-efficacy score with the females. And so they are extremely susceptible to answering these questions in a negative way. And our instructional practices are a big part of that. So if we are genuinely concerned about physics education for everyone, that the ideas that we teach in the physics classroom are important for everybody in our society, then we have to take these issues very seriously. And it comes down to our day-to-day pedagogy, along with our mental approach towards, I'm going to create a learning environment that maximizes the possibility of success for all my students. These are the Ontario figures. Start grade 10 science, the gender ratio is 50-50 as you'd expect. By the time you get to grade 11 physics, the numbers are down to about 38%. This was true in my school a number of years back. And you get to grade 12, it's down to 32. So there's a lot of work that we as a community need to do to address this problem. And it's not just a feel-good issue. It's about trying to help our students and the wider world understand what problem solving really needs. In order to tackle the most important problems that our world faces nowadays, we need genuine diversity in the people who are tackling this problem. And so we need a diversity of thinking. And this comes from people who have very different life experiences from our own. People who have very different priorities and goals based on those life experiences. And this is what helps them to bring different thinking to tackle these problems. And so this is a slide right out of a lesson that I give to both my grade 11 and grade 12 students. As we talk about this in class, it's really important that we encourage everybody to take physics and to stick with it. But they're not going to if we are not teaching them in a way that helps them to learn. So that's my moralizing sermon for this part of the workshop. And now I want to go back to the pedagogy side of things. When it comes time to take our scientific models and tackle or solve a problem, we need to give our students a very structured framework to help them go through the thinking process, to develop the habits of mind that us experts have. So we introduced this, I think it's about lesson 6 of our grade 11 physics course, where we put together pieces that we've been learning so far in the class into a full solution process. So this is how we, on paper, construct our models of some physical phenomena. And there's extras in case anybody wants a bonus souvenir for taking back to school. So this is a lesson that we go through, where we show the students how to structure their thinking process and how to make explicit many of the habits, the skills, and the thinking processes that us experts have. In particular, this process has a lot of what we call sense-making tools built into it. And in a very general way, a sense-making tool is just a strategy that we use to somehow make sense of the scenario that we're given or the work that we do. So what I want you to do with your group is you can assign yourself roles, just like we do in my classroom if you like. So we have our students choose roles every day. One student gets to be the manager of the group. You can inspire your group and lead them to greatness. One person is recorder, so we've got the portable whiteboards on your table there. One person is the speaker who will talk on behalf of your group. And if you have a fourth, and some people have a fifth here, so you can have like a pair of motivators cheering on the group. So this is the task that I'd like us to perform. And we're going to take about 4 or 5 minutes to do this. I want you to look through this lesson and try to identify what are the sense-making tools that are built into the process. What are the steps, the procedures that force or encourage students to make sense of either the scenario itself or the work that they're doing. So choose a role and then record your ideas on the whiteboard. Just be very brief. Please write large. I know it's a smallish kind of whiteboard because we want to be able to hold them up and everybody in the room to read them easily. All right. So we'll take maybe 3 or 4 minutes. Read it through. Sense-making tools. Go. Let's have a quick share of your ideas. Now you have a speaker in your group. I'm sure you've chosen that. So what I would like is we'll just take turns going around the room. If one person can stand up with your whiteboard so that it's above head level so people can easily see. And then if the speaker would just very briefly share one idea, one thing that you've identified as a sense-making tool. So why don't we start off with our group over here.
We like the focus words at the beginning of sentences, or at the beginning of the questions each time, with the guiding words and the boxes highlighting kind of the key ideas that the students should be getting from that.
That's kind of like a checklist there.
Yeah.
Thank you very much. Sean's group?
Okay. Well, all of the ones there, I can pick any one really, I suppose.
Pick your favorite.
The pictorial diagram, like that's one of the smaller checklist things that we could use as a sense-making tool.
Thank you very much. From a cognitive science point of view, pictures are a very powerful sense-making tool. Thank you very much. Our next group. Yes, please.
I guess that's we kind of want to piggyback on the back of these making pictures. So in the pictures, we're identifying specific events that are happening in the situation.
Great, thank you very much. So it reminds the students to think about their model and the interval of time involved. Great, great. And Cindy's group at the back?
We're faking it because we just wrote that down now because we had nothing. Complete honesty. But the discussion was, I think, that all of whatever the strategies are, all these different ways of looking at it, help them look for consistency between the different representations. And when they find a disconnect and a lack of consistency, that's when they know there's something wrong and they need to go back and figure out what it is. They know what to expect, and when they don't find it, they're aware of that.
Is that a feature of an expert's thinking process? Absolutely. Absolutely.
So I think
Carolyn's group.
I think we're running out of things of new things. Yeah, we also have multiple representation. So just all the language clearly explaining the intention of the equations and all of that, and also okay, yeah, I guess we can put it down. Leave stuff for you guys. That's my thing.
Thank you. Elizabeth's group?
Okay, so the one we chose elicits ways of modeling physics, so different ways, not just an algebra method, which a lot of students do. So there's the graphs, you got the pictures, word representation, so the students are always thinking the modeling of the physics and mathematics, how it comes together.
And the educational folk like to call that multiple representations. Great, Gary.
Well, if I was looking at this, I would just role playing, like visualizing what's going on. Forget the numbers. Like that's the first thing I would do when I look at that.
Good, good. How much physical thinking do students need to do before they do mathematics? If you follow this process step by step. An awful lot. And that's a lot of sense making going on. Focus our attention on part D. What are the special sense-making tools that we use here? Yes, sir.
I like that there's like titles or labels on the calculations they're doing, so that actually have to explain like the time to swim the remaining distance, so tell me what they're actually calculating.
Students are not allowed to write down math unless they first state what this calculation is about to do. Sense-making tool. Sean.
Okay, what is very glaring to me, instead of the kind of concluding statement, you're not saying it took Penny 53.52 seconds. Do you make them say, according to this model, I predict it will take her that length of time? That's intriguing.
That is what I encourage. Because I once had a student come up and ask me, why do we do this? I mean, once we calculate it, doesn't that make it real? And that, from a metacognition point of view, is really fascinating because it helps highlight for me their understanding of this process. Like, this is not a real physical thing. This is a mental model that we are deploying in our attempt to understand or make predictions about this situation. And again, as experts, I think it's really important that we unpack what we are actually doing and we provide the proper labels to describe it so that our students are able to use these ideas productively. And you're about to go through an example of this. So one of the things I want to finish by mentioning is that in physics, The purpose of mathematics is to make our understanding more precise. But the understanding has to be there to begin with. Right? If you do the math without any understanding, right, there's no sense-making going on, we are not learning about our world. So, moving on. So sense-making tools, we did a fantastic discussion. And now, you are ready to tackle a challenge. So, what I have set up over at the corner here is a situation that might be very familiar from your physics studies or your classroom. We have a cart on a track, there's a pulley, and a hanging mass. So, when I hold this cart at the end, so it's right up against the motion sensor, and I release it, it's going to move along, reaches a barrier here. The challenge that I want you to complete right now, and I'll pass out the sheet for it, is predict the speed of the cart at the moment it makes contact with the barrier. This is your challenge. When your group reaches the right time, you might want to come up here to make appropriate measurements of the system. This is exactly what we do in my class. And that will give you the data that you need in order to perform or finish off your calculations. Now, there's a lot of you here. So don't all rush up at the start, because you can often save for later in your discussion the actual coming up and getting those measurements. So I'll hand out the sheet. This is almost identical to what I use in my class. I changed it a little bit, just so some features would not distract you from your main task. Now, don't feel that you need to write this up beautifully, which is what I would insist on my students. I'm fine if you talk through the important ideas as you go along the page, and then you might want to jot down a little bit for the calculations. When you're ready, come on up to the front and test your prediction. Go! All right, thank you very much. So, if we take a look at our data, we're getting a speed. Right there's our fastest speed, right about there. 0.99 meters per second. How many people got that?
I'm not failure, sir.
Oh, shit. Shit. What's going on here? No, nobody? This is a real problem, because our prediction does not agree with our measurement. Does this ever happen in science? And this is one of the most exciting parts of science, right? When your theory doesn't agree with your experiment. So, what is the problem here? Is it the experiment or the theory? Or, I should say, the model?
I think it's the model. Einstein's not that real.
So how could we repair our model, or maybe we should say, how could we improve the model to refine it?
Change your assumptions.
What assumption did we make, especially when we reached this stage in our reasoning process? What assumption did we make about our system, or the objects in the system?
No friction, no stretching of the string, no mass of the spring.
Great. So, a very important part of comparing measurements with our scientific models, and if you flip your page, you can see the questions that I ask my students, because they all get a result that's a bit larger than the actual measurement. And so, is that actually reasonable? If we incorporated friction into our model, what would happen to our velocity prediction, our speed prediction? It would get smaller. And in fact, you could make a quick measurement of the rolling friction along the track here, and add that into your model as an extension. And you still won't get this result. Because you haven't taken into account the pulley. But now we're starting to think more like a scientist. And this is what we want to encourage in our students. It happens so often that our measurements do not agree with the calculations we ask our students to make. And we want to give them the mental apparatus, the mental tools for assessing why. Is it a problem with our assumptions in our model? Is there something that we should add in or take away to improve it? When you give your students this language, this framework to think about it, then they can say, oh, it's disappointing that my answer wasn't exactly right, but it still makes sense, right? It should be smaller. The measured results should be smaller than the prediction. So yeah, okay, we're on the right track here. So this is a very valuable part of encouraging that expert-like thinking. So just to wrap things up, because we're into extra innings here. So for this new approach to teaching forces in motion, it's critical for us to do our job really carefully. We have to break down the skills and the habits of expert thinking. So events, intervals, good examples of that. Scientific models, assumptions, and provide them with the sense-making tools that we all use and allow them to practice these sense-making tools, these thinking processes in a meaningful, deliberate way. And that is the way that we can ensure that the vast majority of our students are developing the good habits and thinking skills of a practicing scientist. So thank you very much, ladies and gentlemen. If you head to my website, you can download all these lessons, all my resources. This presentation isn't there yet, but it'll be there shortly if you want to download it for your reference in the future. I didn't have a chance to hand out this page showing our force and energy rubrics, which we use to help students metacognition. Feel free to grab that on your way out. So thank you very much, everybody.
Don't leave yet, because you still need these blue slips. And on behalf of the OAPT,